It's science, but not as you know it. The Naked Scientists.
Hello and welcome to The Naked Scientist with Ben Valsler and Diana O'Carroll.
Hello.
This week we're sitting in for Doctors Chris and Co, who are off enjoying their summer break. We'll be bringing you the best bits of science from across the world, including interviews from the American Association for the Advancement of Science conference in Boston and the Royal Society Summer Exhibition in London.
This week we're looking up to the stars to explore the science of space. We'll be discovering how, compared to the age of the universe, planets form from lumps of rock in the blink of an eye.
If you have a bunch of rocky things of order a kilometre in size, then hit a go button, gravity takes over, and they will, on timescales of tens to hundreds of million years, form most of the planets and the complement that we know in our solar system.
We find out why the James Webb Space Telescope will bring us great data for scientists to work with, as well as great images for poster printing companies.
It's so spectacular in its capabilities that we expect miracles to be found, surprises to abound in the data, and beautiful pictures as well.
And we'll discover the British-made Mars rover ExoMars and find out why robots may not take the place of man in future space missions.
It's what you might describe as a frontier spirit. It's about exploration. In terms of exploring the solar system, there's a real drive, real excitement about man walking on the moon, or perhaps ultimately walking on Mars.
Now, although Chris and Co are away, we've invited Sarah Castor-Perry, star of our Science on the River show, to act as custodian of your questions. She'll be dropping into the show later on to answer your space-based questions.
All this, and we'll be challenging Dave Ansell to build a kitchen science space rocket. But can he get into orbit?
So do keep your questions coming in. Chris will be back in September to take them all on. Get them into us by email at chris@thenakedscientists.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Later on today's Naked Scientists, we'll be finding out how astronomers use winks, wobbles and blips to discover exoplanets. These are planets orbiting around a star outside our solar system. But first, we'll go back to a conference held in Boston earlier this year by the American Association for the Advancement of Science. That's the AAAS. Now, while Chris was there, amongst some of America's finest minds, some of whom have brains the size of small planets, Chris met up with Michael Meyer to discover how real planets are made.
Some of today's presentations at the AAAS Science Conference here in Boston were quite literally out of this world, and that's because scientists are explaining how they're looking for Earth-like planets, in other words, other worlds that could harbour life elsewhere in our Milky Way galaxy. But how do planets form in the first place, and why are they all different shapes and sizes? Well, earlier today I caught up with Michael Meyer, who's been trying to solve this planetary puzzle at the University of Arizona.
I study star formation and planet formation. In particular, the last few years we've been using NASA's Spitzer Space Telescope to understand the formation and evolution of planetary systems. So we pick groups of stars that are very young, groups of stars that are middle-aged, and groups of stars that are older, and hope that we're watching a movie of what unfolds as one cohort evolves into the next and into the next.
And this gives you some clues as to what's going on 4.5 billion years ago in our own solar system, in other words, how we got here.
That's what we hope. Our program is specifically focused on studying sun-like stars in the disk of our Milky Way galaxy. And we have a sample of 300 stars with ages only 3 million years after the stars first formed, up to 30 million, 100 million, 300 million, a billion, and then up to 3 billion years old, not quite as old as our star, the Sun.
So how long does it take a system of planets to form in the first place?
Well, it depends on which kind of planet we're talking about. Our program has been trying to study the evolution of gas and dust content. On the gas front, we've determined that the amount of stuff needed to form Jupiter-mass planets goes away on timescales of 3 to 10 million years, so that a planet like Jupiter has to form really fast. We think planets like Earth probably took 10 to 50 million years to form, at least in our own solar system, and the new data we've received from the Spitzer Space Telescope suggests that those processes might be very common around sun-like stars.
That's not very long, though, is it? That suggests that once planets are going to happen, they happen quick.
That's right. If you sort of have a bunch of rocky things of order a kilometre in size, then hit a go button, gravity takes over, and they will, on timescales of tens to hundreds of million years, form most of the planets and the complement that we know in our solar system.
So what's the sort of step-by-step system of events that seems to happen to give rise to planets once a star begins to form?
Well, the disk of gas and dust that's left over from star formation is really a key part of that whole process of forming a young sun-like star. And over time, the gas and dust evolves in that the particles, the little dust grains that give a lot of the infrared emission that we see, can smash into each other and stick. It's kind of like the particles are the soot that you see rising from chimneys. Those tiny, tiny particles come together and form larger and larger things like pebbles and rocks, and eventually into things that we might identify as boulders, and then grow up to objects as large as the Moon and Mars, and that is the cascade of collisions that we think leads to planets like Earth.
Why are all the planets on the same plane, though? Why do we find that they all go round lined up? Why does all that material settle into a disk, I suppose, rather than just planets here and there all round the star?
If you imagine our star like the Sun forming from a cloud of gas and dust in space that's rotating, albeit ever so slowly, as that cloud contracts, a lot of the material is forced into a disk by a principle of physics known as the conservation of angular momentum. It's the same thing that whizzes you to the outer edge of your car as you're speeding around a curve in the motorway. That same physical principle, it operates on spinning clouds of gas that form sun-like stars, and it almost forces you into a situation where you collect mass in the center, but then you must be surrounded by a disk of material left over.
And what makes the difference between whether we end up with a planet a bit like the Earth or one that's mainly gas like Jupiter? How does that happen?
Well, even to form a planet like Jupiter, you need to start with a core that is probably looks similar to something like a few to 10 times the mass of the Earth. The processes that lead from those tiny dust grains up into pebbles and boulders and things like the Earth take a certain amount of time. And if you can get 10 Earth masses of rocky material together about the distance of Jupiter from its sun before the gas goes away, you have the potential to sort of serve as a focal point, a nucleation site, if you will, of swarming and gathering the gas together. If that process takes too long and the gas is blown away before it can happen, you might not have a Jupiter. But Earth-like planets, we think, form anyway. Whether there is or isn't gas there, you can still, over a more leisurely period of time, 10, 30, 40, 50 million years, form rocky planets. And we think that's one reason why we're seeing evidence of planet formation like rocky planets like Earth much more common than the evidence so far that we see for gas giant planets.
Is there any kind of magic formula where you always end up with planets that are certain sizes, or are you now finding that in fact it's just a mixed bag?
Much more so a mixed bag. Our ideas of planet formation suggest that it's messy. It's a very complex process, and we think that's what leads to the large diversity of planetary systems that we see around stars like the Sun.
So does that, or how does that affect our prospects of finding another Earth-like planet out there somewhere?
Well, as I said, we think our research suggests that planets like Earth could be very common. Now, like Earth simply means that they're rocky and that they're relatively close to their host star. Exact analogs of the Earth are probably rare, but what is it about the Earth that gives the possibility for the emergence of life? That's what all of us would really like to know, and would help us to better assess whether the 60% of sun-like stars that we think might be forming terrestrial planets, whether those rocky planets could be the places where life could develop.
Do you know what those magic ingredients are?
The elemental compositions that lead to life? Well, we have a favorite word that we use in the emerging interdisciplinary field of astrobiology, that it's CHONSP: carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. And those are the elements, the stuff of life that leads to the biochemistry of life.
And is it, based on your measurements, likely that most of these rocky worlds that form around planets will have a fairly even smattering of those, or are there special, again, accumulations of certain things in certain places that happen?
The chemistry of forming planetary systems is very complicated, and we believe in a general way that the farther out you go, the more likely you are to retain the carbon, nitrogen, and oxygen in icy materials that could be very important to the emergence of life. In the inner part, it's a bit of a mixed bag. The chemistry and the dynamics are so complex, I can imagine a wide range of compositions for terrestrial planets.
And is it just stars a bit like our Sun that we think give the best prospects for the evolution of life eventually? Or could we just be looking at any old star and hope to find some life there?
Well, I think our In our ignorance, we focus on things we know, and so we only know of one planet that has given rise to life, so we focus on terrestrial planets and we focus on stars like the Sun because, again, in our ignorance, that's what we know. I think over the years we're getting a sense that our perspective is a bit myopic, that we need to step back and look at the formation and evolution of planetary systems around a whole host of stars. We shouldn't forget that the very first planets were discovered around the dead remnant of a very massive star, a pulsar, and that the first rocky terrestrial planets were in fact found in such an extremely exotic environment. As we learn more about how planets could form around stars much less massive than the Sun, the cold red M-dwarfs, those are the most common stars in the Milky Way galaxy, and if they are suitable places for life, then life could be much more common than we even could imagine.
And I have to ask you to speculate at that point. What do you think the chances are during your professional life that we're going to find it?
I don't know. What I do know is that in the coming decades, we will learn a tremendous amount about how common Earth-like planets are around stars like the Sun, and whether or not we detect the biochemical signatures of disequilibrium, which is really the stuff of life in the atmospheres of planets around other stars. I can't venture a guess, but I do believe that the biochemical origins of life will remain one of the key problems in science for the next century.
The origins of life are a tricky one to tackle, but who knows when we'll get there. That was Michael Meyer from the University of Arizona telling Chris about his work on the origins of planets. So, we found out a great deal about how stars and planets form over millions of years, but sometimes we need to get down to the ground level to really see what's going on right now. This is exactly what we've been doing with things like the NASA Phoenix mission, which has recently found the first physical evidence of water ice on Mars. The science we're getting from Phoenix is great, but Phoenix can't move to explore different parts of the planet. ExoMars is an all-purpose rover designed by the European Space Agency and scientists at the University of Leicester, including John Bridges, who met Mira Senthillingham at a recent Royal Society summer exhibition.
So here we have the ExoMars engineering prototype, 6-wheel drive, rugged all-terrain vehicle which can go up and down 45-degree slopes and over large boulders. So ideal for Mars. We're developing the science instruments like the stereo cameras so we can build up three-dimensional views of the Mars surface and look at the rocks and decide how they formed.
So will it be taking any actual samples and analysing them?
It has about 25 kilograms of science instruments, different spectrometers to look at the chemical compositions of the rocks and the mineralogy, so we can find chemical and mineral signatures of water on Mars or life on Mars. So this is a real motivating factor for scientists and really, well, I think the population at large to ask the big question, was there ever life elsewhere in the solar system? And if we're going to address that question, we need rovers like this with lots of science instruments.
What will ExoMars be exploring?
ExoMars will go to a new place on Mars that no one's been to before. It'll be looking at rocks, looking at the textures, looking at using its microscope, looking at the subsurface structure with a seismometer, find out how the rocks were deposited, were they deposited from water or from wind. As we piece together bits of information like that, we find out what was happening on Mars millions of years ago. Today, Mars is cold and dry. Millions of years ago, or billions of years ago, we think it was probably warm and wet. But we don't know for how long it was warm and wet. So these are important questions to find out about Mars if we want to answer, ultimately, was there ever life on Mars, and why did climate change on Mars from warm and wet to cold and dry?
And when exactly is ExoMars set to go?
2013. It'll take 9 months to get there.
How do you actually go about testing this to make sure it will work and survive on Mars?
Well, for instance, the engineers from Astrium who are building the ExoMars prototype take it out to Tenerife and they practice with it over all sorts of rocky terrains to simulate the Mars surface, going up and down 45-degree slopes over rocky terrains, making sure it can do what we need it to do on Mars.
And how about the actual environmental conditions, temperature and things like that?
Well, Mars is a really extreme environment. The average surface temperature on Mars is about minus 60 degrees centigrade. And at the poles on Mars, it can go down to minus 140 degrees centigrade. Just to put that in context, the lowest ever recorded temperature on Earth is about minus 80 degrees centigrade. So it's a very cold and very dry place. Also, the atmosphere is very thin. It's about something like 1,000th of the atmospheric pressure of that on the Earth. That means a lot of the radiation from the sun can get through to Mars, which would actually be stopped on Earth. So it's a much more harsh radiation environment. That means organic compounds are broken down on the Mars surface, whereas on Earth they would be preserved. That's why we've got a drill on ExoMars, so that we can get down fairly deep into the subsurface, into areas which haven't been cooked, if you like, by the sun's radiation.
So are robotics the future of space exploration?
Well, that's actually the question we're posing today, because our exhibit is called Exploring the Solar System, Mankind on Machine. Should we continue with robots and get lots of great science, but should we also perhaps have a UK astronaut training programme? So we're trying to gauge here what people think. We've got a little poll here, and what we found this week is that the majority of people think that we should explore the solar system both by mankind and machine. We should have both.
So what are the benefits of humans and the benefits of robots?
Well, robots, perhaps you get more science for your money, if you like, immediately. It's less risky. You're not going to risk people's lives. And you can send probes perhaps into really extreme cold environments or hot environments, etc. It would be very, very difficult to send people. Certainly over the next 10, 20 years on Mars, it's going to be dominated by, it will be robotic exploration. And the first samples we bring back from Mars, it will be done robotically. So we can start doing tests with rovers and with samples brought back from Mars within the next 20 years. There can be benefits from sending people because they're such flexible machines, if you like, and the autonomy. It'll be a long, long time before robots quite have that. But the sheer scale of the endeavour to get people there will always mean that it is going to take longer. But talking to the people who've come to the exhibit and ask them, well, why do you think we should also send men? And I think there's what you might describe as a frontier spirit. It's about exploration. Difficult to sort of quantify in terms of absolute science, but in terms of exploring the solar system, there's a real drive, real excitement about man walking on the moon or perhaps ultimately walking on Mars. I think that's a powerful driving force, even if it isn't purely scientific. I don't think you can dismiss that. So I think exploring by mankind, yes, we should do it, but to me it's more of an exploration thing rather than purely scientific. So it's great, but it's not just about science.
That was John Bridges talking to Mira about the technology that's gone into the ExoMars rover and how he feels that no amount of technology could ever make up for the thrill of sending men, or women of course, to Mars.
Laying the facts bare, the Naked Scientists.
Space instruments like the Hubble telescope have been vital to expanding our horizons, quite literally, but the next generation of space telescopes will have to take us even further. Staying at the AAAS conference, Chris met up with John Mather, senior project scientist for the James Webb Space Telescope, to find out what questions this new breed of instrument will need to tackle.
Well, I think the number one question is, how did we get here, and are we alone? So the astronomers can tackle some pieces of this question by looking at the first objects that formed after the Big Bang, looking to see how galaxies are made, how stars and planets are formed from their gas clouds, and finally, how did the Earth come to be like it is?
And how are you hoping to answer those things?
Well, we have in mind a telescope which will be much larger and more powerful than the Hubble Space Telescope, and it would be launched in 2013. Into deep space by a consortium of NASA leading the partnership with European and Canadian space agencies, and pieces from around the world coming together to make this happen. So launch in 2013 on an Ariane rocket from French Guiana near the equator.
When you say deep space, why can we not just put it in orbit around the Earth?
We need to put the telescope far from the Earth so that it can cool down to a low temperature, so that it can detect the infrared radiation that is now the new frontier in space astronomy.
Oh, that's interesting. So why do you want to look at infrared? It seems paradoxical to look at light that we as humans can't see. I suppose that's just because we as humans get used to seeing things we can see rather than seeing things like infrared we can't.
Well, yes, the new technology has opened up a new window for us. So infrared light comes to us from the most distant parts of the universe because of the expansion, which causes something we call a redshift. Also, we get to look inside clouds of dust and gas where things are cooler, where they're not warm enough to emit radiation that we could see with our eyes, but they still put out immense amounts of heat radiation. So if you wanted to see yourself at a great distance, you might use an infrared telescope.
So where will this telescope actually go? How far from Earth have you got to put it out there?
Well, it's put out 1.5 million kilometers from Earth, a place called Lagrange Point 2, which orbits the Sun along with the Earth every year.
And how's it powered? Solar?
It does receive power from the Sun with solar cells.
And what major experiments will it be doing, this telescope?
Well, it has 4 instruments on it, cameras and spectrographs to cover the entire range of wavelengths from 0.6 microns, which is red light that you could see with your eye, way out into the near and mid-infrared. So these 4 instruments will be able to look at distant galaxies, stars, planets, clouds of gas where they're being made, and even little objects in the outer solar system.
And dare I ask, what's the price tag?
The life cycle cost from the first day to the very last is $4.5 billion, which is actually less than the similar tag for the Hubble Space Telescope, even though the telescope is much more powerful.
And when you say lifetime cost, how long do you anticipate you'll be able to use this?
It'll take about another 5.5 years to get it to launch, and then we expect to run it for 10 years.
That's quite cheap, really, isn't it? So on a 10-year running cycle, that's not bad.
Well, for what it can do, it's quite cheap. It's so spectacular in its capabilities that we expect miracles to be found, surprises to abound in the data, and beautiful pictures as well.
That was John Mather talking with Chris about the James Webb Space Telescope, which needs to be sent deep into space in order to cool down enough to pick up infrared radiation from the far reaches of the universe. Any telescope that was placed closer to Earth would actually be too warm, and its sensors would pick up more infrared from itself than it would do from space. And we can look forward to the groundbreaking science and fantastic photos from after its launch in 2013.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
This is The Naked Scientists with Ben Velsler and Diana O'Carroll. We're sitting in for Chris and the gang while they're off enjoying their summer break and bringing you the finest science from our travels around the world.
Now, don't forget that we beam this programme live into Second Life from 6pm UK time, which is 10am Second Life time. There's a fantastic group of people there who like to discuss the science in the show. So if you want to join them, if you want a chance to talk science in the virtual world, visit the Scilands in Second Life and just do a search for The Naked Scientists. You can drop by our mansion, relax on one of the sun lounges and listen to the show. And while you're online, why not tell us how you think we could make our show even better? We really want to hear from you about what it is that you like or dislike about the show. So we set up a survey at thenakedscientist.com/survey.
And still to come, we set Dave Ansell the challenge of getting a kitchen science-style rocket into orbit. And Sarah Castor-Perry will be joining us to take on some of your science questions.
Now, winks, wobbles and blips sound more like sound effects from a science fiction film than genuine scientific terms, but these are actually the 3 main ways that scientists find planets out in space. Mira met up with the Open University's Carol Haswell to find out more.
What we're doing is just presenting the methods that are used to find planets around other stars. So obviously we're very familiar with the planets in our own solar system, and we've known about those for a long time. We can see them quite easily because they're bathed in light from the sun. Now, to see a planet around another star is much more difficult because the star itself is very bright, so we can't see the planets around another star directly, just as we can't see the planets in our own solar system when it's daytime, when the sun is up.
So what are the techniques?
Okay, well, there's 3 techniques, and we've actually given them nicknames, and the 3 nicknames are wobbles, winks, and blips.
Okay.
So probably the simplest way to understand is the winks method. That works if the planet around another star is lined up so it actually happens to pass in front of the star from our line of sight here on the Earth. And we see this phenomenon in our own solar system. If Mercury passes between us and the Sun, we observe a transit, and there was a transit of Mercury quite recently, just a few years ago. Exoplanets too can transit, and when that happens, the planet is opaque, so it blocks some of the light that the star's emitting. So an astronomer looking at that star would see it appear to get dimmer by 1% or so, and the transit would last typically for about 3 or 4 hours. So what we do is we actually look at as many of the stars in the sky as we can, and we measure their brightness roughly every 10 minutes, and do that for the whole of the time that the star is visible in the sky, so for months, every night that it's clear.
That's a lot of measurement.
It's a huge amount of measurement. So a lot of the challenge in the project has not been the principle of it. It's quite easy to detect a 1% dip in the brightness of a star, but it's in managing the huge amount of data to find, the needle in the haystack, the few stars, where there is a planet that is suitably aligned to execute a transit.
So what's the wobbles technique?
The wobbles technique has actually been historically the most successful way of finding planets around other stars. And the way it works is, if you've got a star and a planet, you think about the planet orbiting around the star, but in fact it's a little bit more subtle than that, because the planet has mass and the star has mass. So in fact both the star and the planet are orbiting around their common centre of mass. And the way to understand what the centre of mass is to think of a seesaw. So in order to make the seesaw work, you need to balance the people on the two ends of the seesaw. If you now imagine a sumo wrestler and a small child on a seesaw...
Not quite balanced.
Not quite balanced. And in order to balance it, you would have to move the sumo wrestler very close to the pivot point of the seesaw. So if you did that, you would find a balance point with the sumo wrestler sitting practically on top of the pivot and the small child at a large distance from the pivot. And the pivot is actually the centre of mass of the sumo wrestler and the child. The planet and the star are very similar. The planet has much less mass than the star, so the pivot point, or the centre of mass, is very, very close to the star. So the planet has a large orbit, which is why we think of the planet orbiting around the star, but nonetheless the star has a small orbit. It's moving too around the common centre of mass, just as the sumo wrestler on the seesaw is moving slightly up and down. So astronomers can see stars and they can measure their motion, and they measure it by something that's called the Doppler effect, which is an effect when something is moving towards you. If it's emitting waves, as it moves towards you, the waves get squashed up. As it's moving away from you, the waves get stretched out. So with light, this has the effect of changing the colour of the light. So as the star is executing its small orbit, like the sumo wrestler, some of the time it's moving towards you and the light is red-shifted. Some of the time it's moving away from you and the light is blue-shifted. And by studying that shift, astronomers can see how big the circle it is that the star is moving around in its orbit. And that then allows you to work out the mass of the planet that it's in orbit with, just as if you looked at your seesaw and measured the distance of the sumo wrestler from the pivot and measured the distance of the small child from the pivot. That would allow you to work out their relative masses. So the Wobbles method allows you to detect a planet and to measure its mass. So if you detect a planet that executes a wink, you know not only the radius of the planet, but you know the orientation of the orbit. So if you then measure the Doppler shift and apply the Wobbles method, you then can know the mass of that planet exactly, as well as knowing its radius. If you know the mass and the radius, you can measure the density. And if you know the density, that gives you a good idea of what the planet is made of.
That's a great amount of information to be able to deduct.
It is, considering you can't see the planet at all. And for me, that's what science is all about, applying the ingenuity of human thought to solving problems and learning things, learning as much as you can.
So what is the third and final method?
The third and final method is the method of gravitational microlensing, and we've given it the nickname BLIPS. And this method depends on the fact that mass curves space, and this is something that was discovered by Einstein when he developed his theory of general relativity. So all of the stars in our galaxy are actually moving, and they're moving sort of roughly in orbit around the centre of the galaxy, but they're not orbiting in a very organised way. So that means, from our perspective, a distant star and a less distant star will sometimes happen to line up exactly. And when that occurs, the light from the more distant star is actually travelling through the space that's been curved by the mass of the foreground star. So the curved space acts like a lens on the background star's light. This gravitational lensing effect magnifies the light from the background star and makes it appear brighter. So it takes about a month for the two stars to come into alignment and then drift out of alignment again. And during the course of that month, if you were watching that bit of sky, you would see the star appear to get steeply brighter, reaching a peak when the alignment is exact, or as exact as it's going to get, and then it declines again as they drift out of alignment.
So then how does this enable you to see the planets going around those stars?
If the foreground star, the one that's acting as a lens, has a planet, and one of the images of the background star that's being lensed by the curved space passes close to the planet, then the planet too has mass. So the planet too curves space and adds its own smaller lensing effect. And then you'd see an additional little sharp blip that actually brightens very dramatically and then returns back down to the smoother curve over the timescale of about a day. And when you see that very characteristic blip, you know that there must be a planet around the foreground lensing star. And from various characteristics, how bright it is, how quick it is, you can work out properties such as the mass of the planet and how far it is from its host star.
How many planets using all these methods have you managed to find so far?
So far, in total, we know of about 300 planets around other stars. They're being found at a tremendous rate. We really are beginning to find these planets quite quickly because the methods are now all tried and tested and groups of astronomers are organised to implement them efficiently.
That was Carol Haswell giving Mira a lesson in planet spotting. Carol did tell us that since she met up with Mira, the number of planets found could actually have gone up to between 350 and 400. So clearly, these methods are working very well. Diana.
Still to come, we'll be coming back down to Earth with a bump, or should that be burp, as we discover the astronomical effort it takes chefs at the Olympic Village who have to run a kitchen the size of a football pitch. That's enormous. Think how many cakes of the week you can make in that. Well, that sounds like quite a challenge, which is exactly what we've set Dave Ansell in this week's Kitchen Science. There seems to be little that Dave can't do with the things he has lying around the house, but we wanted to know if he could get a homemade rocket into orbit. The problem is that we're not letting him use explosives. Ben went to join Dave outside the Cavendish Labs in Cambridge to see if Dave was up to the task. Can he get a pressure-powered rocket into low Earth orbit?
Well, low Earth orbit's a pretty big ask, but we're going to see how high we can get.
Well, it is quite a challenge we've set you here today, Dave, but what is it you're going to do? How are you going to try and get something up into space?
We'll start off with a really basic principle. Okay, I've got here about 8 kilograms of rice in some nice convenient bags. What I want you to do, Ben, is hold it, stand on your heels, and then throw it straight away from you as hard as you can.
And when you say stand on your heels, you mean basically lean back, so put my feet together, put all my weight on my heels.
Yeah, that's right. Take your toes off the ground.
Okay, weight on my heels, and... Ah! That was a trick, Dave, wasn't it? You were just trying to get me to fall over. As soon as I threw them, I went backwards quite quickly, and I only just caught my balance.
Yeah, that's what should have happened. The first scientist to work this out was a fairly famous guy called Isaac Newton. He said that every action has an equal and opposite reaction. And what he meant by that is if you push something, it pushes you straight back exactly as hard as you're pushing it.
So me throwing the bags of rice forward meant that the opposite reaction was for me to be pushed back.
Yeah, the bags of rice pushed you backwards, so you started to fall over.
Okay, so every action has an equal and opposite reaction. But I still don't see how this is going to get us into space.
Well, if you imagine throwing something downwards, it's then going to push you upwards. And if you throw it down hard enough, you should go upwards. That's basically how all rockets work. They throw stuff downwards, they go upwards.
Are we doing this with bags of rice?
Okay, we're not going to be using rice, but what we're going to need is a lemonade bottle and a pump and something to stabilise the lemonade bottle.
Now, NASA and the European Space Agency have budgets to get into space in the order of millions and millions of dollars. This sounds like you spent about £2.50.
Yeah, pretty much.
We're over here at your launch pad, which actually appears to be a very simple wooden scaffolding that's holding upright an upside-down lemonade bottle. What are we actually going to do?
Well, the first thing we're going to do is basically just pump air into this bottle and keep pumping until the bung, which is holding the air in there, falls out, and then we'll see what happens to the rocket.
Well, the bung we've got looks like the stuff that I used to use in my chemistry lab at high school. It's a proper orange rubber bung. I'm sure you'll have seen them in the top of test tubes. That's not that easy to get hold of. What if people wanted to try this out at home?
Well, you can sometimes get them from winemaking shops. Otherwise, if you can't get hold of one, you might be able to make something very similar using a normal cork and putting a couple of layers of the fingers of a rubber glove over the top. And then the other important thing you've got to do to the bung, whatever it is you've got to get air in through it. So there's a couple of ways of doing that. You could use one of the little needles you use to pump up footballs and put that through the bung. Or what I've done is got a valve out of a bicycle tyre and then drilled a hole through the bung and put that through. Makes it a bit more secure.
So the important thing is that the bung is a good tight fit in the bottle and you have some way of getting air through the bung into the bottle.
Yeah, that's right.
Well, by the sounds of the thunder, we only have a very limited launch window today before the storm sets in, so I guess we better start pumping up our bottle.
Now I'm going to push this bung really firmly into the bottle, because the thing which actually controls how much pressure we can build up in the bottle is how hard this bung is jammed in.
And I can see you're using a fairly standard bicycle stirrup pump here. Does the type of pump you use matter?
Probably don't want to be immediately over the bottle, so ideally something with a fairly long tube on it, so that you've got a bit of space between the bottle launching and yourself.
OK, well, this is our first trial. I doubt this will quite get us into space, but let's start pumping and see what happens.
OK, off we go.
Well, that bottle shot off into the air. I didn't even see where it went, but I can see that it's landed behind us. Dave, how high did that go?
It went up to about 10 metres, probably.
Well, that's not bad for our first try. Is there any way we can make this a bit better?
Well, at the moment, the bottle is just pushing out air, and air's really light, so it's not going to get pushed upwards very hard. If we put something in the bottle which has got a bit more mass, a bit more density, then it's going to push something very heavy downwards, so it's going to get a much larger force upwards. So hopefully it should go a bit higher.
So if we fill the bottle completely full of water and then pump that up, then there's lots of mass coming out of the bottom, large opposite reaction, so it should go really high in the air.
We can certainly try it.
Well, let's fill the bottle with water.
OK, so that's about 4/5 full now. We'll see how that goes.
And the same thing applies. We push the bung hard into the end and then start pumping it with a normal bike pump just to fill it with as much air as possible. When the pressure inside is too much for the bung, it'll shoot off, it'll push all the water downwards, and it should go quite a long way into the air. So I'm going to stand back a bit for this one, Dave. Get pumping. Oof. Well, that was certainly impressive, but it didn't really go as high as the one with just air. I thought having the weight in there would give it a bigger opposite reaction to the reaction of water pushing down, and so it would go higher.
Well, there is more force because you are pushing something much more dense outwards. The thing is, the rocket is now a lot heavier, and you've got less energy stored in the compressed air because there's a lot less air there. So there's not enough energy to make the rocket go high enough if you put in too much water.
OK, that was 4/5 full of water, and it went about 3 metres into the air, which isn't a lot compared to the 10 metres of the empty bottle. So should we just put a little bit of water in?
Yeah, normally somewhere between 1/4 and 1/3, it depends how hard the bung's pushed in, is ideal for a water rocket. In this case, I'm pretty confident it should go well. There's no point in getting up high if you can't see where you've been. So I'm going to try and attach a camera to the top and get the camera back down without smashing it.
So just like NASA and the ESA attach very sophisticated recording equipment onto their rockets and their landers, we're going to tape a camera onto the side of our bottle.
Yeah, a very cheap digital camera.
Will it land safely? How will we get it down?
I'm going to attach a parachute to the top of this digital camera, so there is some chance of it getting down in one piece.
And if it does come down safely, we'll put a video of this on thenakedscientist.com/kitchenscience. And it's about to rain, Dave, so we are losing our launch window, so let's get pumping. Wow!
Oh, beautiful.
The parachute has worked absolutely beautifully, and it is drifting away on the wind. Dave's having to run off to pick up the camera before it gets lost completely, and the rain has really set in right now. So we'll go inside and talk about the physics of how this has worked. Well, we've managed to find a bit of shelter from the rain, and we can still see our launch pad over there getting very heavily rained on. Running away from the rain is not something you often see NASA scientists do, is it, Dave?
In general, they tend to try not to launch in too bad weather.
Well, obviously we had our budget constraints and our time constraints, but still, that was quite impressive. What sort of pressure was inside that bottle?
The bungs tend to come out somewhere between 1 and 2 atmospheres of pressure, so not a huge amount, but enough to push that water out really quite fast.
So that would mean that there would be 3 times as much air inside the bottle as there would be if we just left the lid off.
Yeah, that's right, and then that pushes down on the water in there really hard, pushes the water out really hard, then the water pushes the rocket back upwards, and the rocket flies upwards really fast in that impressive way it did earlier.
Well, it was very impressive, and I'd say it got to between 15 and 20 metres, I think.
Something like that, definitely. That is pretty impressive, but various people have managed to launch rockets up to maybe 1,000 feet, so 300 metres.
So obviously the real space agencies, they do this using completely different methods. How do they do it?
What they do is they burn something. The highest energy chemical rockets, which you'll see, burn hydrogen in oxygen to form water. So same principle, but the water's coming out at least 2,500 degrees centigrade. So it's basically in the form of steam, and it's coming down far, far faster than the water we're using in our water rocket.
And that provides the downward force, the opposite force of which pushes the rocket up through our atmosphere and out into orbit.
Yeah, that's right. And because it's coming out so fast, you don't need so much of it to produce the same amount of force, so the rocket can last a lot longer and get you all the way up into orbit.
So how fast do you need to be going to actually get into space?
Well, getting into space is actually quite easy. All you've got to do is get up 100 kilometres, and then you're technically in space. The problem is, if you're just sitting there at 100 kilometres upwards, you're just going to fall straight back down again and hit the Earth, and end up as a kind of lump of mush in the bottom of a field somewhere. However, if you want to stay in orbit, you've got to be going really quite fast. You've got to be going at about 24,000 kilometres an hour, because actually when you're orbiting, you're always falling. The trick is you're going sideways so fast that by the time you would have fallen through the Earth, you've actually gone all the way around it and missed the Earth entirely.
So what about the missions that we send out to Mars, or the probes that we've sent even further than that? Surely they can't just rely on the same trick.
No, they don't. They've got to have enough energy to actually escape the gravitational attraction of the Earth.
So is that what we call escape velocity?
Yeah, that's right. Escape velocity is just going fast enough that you have enough kinetic energy to escape the Earth's gravitational field.
So if we need to be going 26,000 kilometres per hour just to stay in orbit, how fast is escape velocity?
Well, if you're going straight upwards from the Earth's surface, it's about 40,000 kilometres an hour.
That's very, very fast. It's no wonder they need such powerful rockets.
Yes, getting that speed requires a huge amount of energy, but actually most of the fuel in the rocket is actually used lifting other fuel, and that's the reason why rockets are so enormous.
So when you factor in the weight of all the equipment they have to take as well, does this mean there's an upper limit to actually how far we could send a rocket?
It does mean that practically we're never going to get a chemical rocket out of the solar system. You'd have to use something with much more energy per unit mass of the fuel, so either a nuclear-powered rocket or some kind of crazy light-powered rocket, yes.
Well, it sounds a bit like we might be getting into the realms of science fiction now instead of kitchen science. So let's come back down to the Earth with a bump, unlike our camera. Now, don't forget, we'll put the video from our rocket launch on thenakedscientist.com/kitchenscience, where you can also find all sorts of different, slightly more earthly experiments that you can try out. And that's it for Kitchen Science this week. We'll be back next time.
A valiant effort, even if 20 metres is a little bit short of orbit.
Now, I've seen lots of bottle rockets set off before, but the thing I didn't realise until I did this with Dave is that the main limiting factor is actually how hard it is to push the bung out. So the more pressure it takes, the higher the rocket will go. Now, as well as our own bottle-mounted camera, which got some fantastic shots of the Cavendish lab, the Fracture Group at Cavendish were kind enough to lend us their high-speed camera. Now, this means that we could video the launch and see it in glorious slow motion. It really does look like a proper NASA rocket launch. We will put the videos of that onto thenakedscientist.com/kitchenscience, and that's also where we put quite a lot of videos of the experiments that we do. So if you want to try them out, you can see what should happen, but if you don't have the equipment, you can also see exactly what we did.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
Even the astronauts and cosmonauts on the space station can't avoid hearing about the Olympics. But rather than harp on about the prospects for medals or the politics surrounding the event, we thought we would look at something close to the athletes' hearts, their stomachs. Feeding the globe's Olympic athletes is, as you can imagine, a mammoth task. There are 28,000 people in the Olympic Village, and over the next 2 weeks they'll eat an estimated 3.5 million meals. On the menu, 243,000 kilos of meat, 800,000 eggs, and more than 900,000 bananas. They say that if you placed all of those bananas end to end, they would cover the Olympic marathon route 3 times over. Don't you love those useless statistics?
Yes, I wonder actually how far it would cover if you were to straighten all the bananas out.
Well, according to the European guidelines on straight bananas.
Well, exactly, yes. So that's a lot of bananas they're going to get through. So how are things in the kitchens?
Well, in the kitchens, things are very real and very intense. 230 chefs and 6,500 Chinese student workers will be pumping out the Olympic food, as Madeleine Jenner reports.
In the Beijing Olympic Village, anticipation is building. The athletes are preparing to represent their countries, and Irish-born Sydney-sider Gary Leahy is gearing up to serve millions of meals. Gary Leahy is Senior Executive Chef at the Olympic Village. He arrived in Beijing just over a month ago in preparation for his third Olympics.
The first 2 weeks were pretty good because obviously there was no athletes here, so we managed to get in a lot of sightseeing, and I'm very, very impressed with Beijing as a city. So then, obviously, the athletes started to come in, and we've just been working so hard the past 2 weeks. We're doing about 33,000 meals a day, and we'll peak to 60,000.
The dining hall at the Olympic Village, I understand, can sit some 6,000 people. And so I presume the kitchens are pretty large too. Yeah, the kitchen is must be the size of a football field, or close to it. We have the kitchen set up into 5 sections, and obviously each section has their menu, and then they fire the food, basically, and my job is I'm the expediter, and all the food comes through me, and I'm the link between the kitchen and the front of house.
And on the menu, there are plenty of options. For breakfast, there's scrambled eggs, sautéed zucchini, chicken with chickpeas, octopus with peppers, red miso and congee. Gary Leahy again.
There's obviously a big Chinese influence here, which is very popular, and Chinese influence at actually all the games would probably be the most popular food that we do. I mean, there's stir fries and there's soups. Like a lot of Chinese, but a lot of Mediterranean dishes or, European-based dishes. So, yeah, everybody is served across the board, no matter what sort of a taste or a background you come from. I think we've got it pretty much covered.
And, I mean, of course, you're also dealing with athletes who, most of whom would have very strict kind of diet regimes. I mean, how do you account for that?
We probably have about 80 different items on the menu every day or every meal period, and we also have halal stations, and we have designated equipment in the kitchen we just cook pork in them, and we've designated pork cool rooms. So we're sort of covering every base, really.
And since the Sydney Olympic Games, food security has become a much bigger issue. In Sydney, all the food came direct from the suppliers every day. But in 2004, in the wake of terrorist attacks like 9/11, security was much tighter. In Athens, all food went to a warehouse first for security checks. And in Beijing, the authorities are leaving nothing to chance.
Food safety is really, really tight, and obviously the Beijing government have people in the kitchen as well, temperature checking, taking samples. We were at the Beijing Hygiene Bureau about 2 weeks ago, and they were talking us through that even the suppliers that the Beijing government has employed to supply us with food, there's people there from the Hygiene Bureau tracking all the food. So literally from the farm to the fork, the food is tracked by Hygiene Bureau people to make sure that everything is just in top shape.
As the Games draws closer and closer, I mean, what's it like being in the village? I mean, obviously you've got a huge task ahead of you, and it's a very different task to the athletes, but it must be getting pretty exciting.
Yeah, the village is it's a buzz. A lot of athletes walking around, as I say, when we're leaving work every day, just strolling down the streets with all these athletes. It's really quite amusing, But yeah, the buzz in the village is just fantastic. They're all athletes are hanging their flags out of their apartments, and it's really good.
That was Gary Leahy, Senior Executive Chef at the Beijing Olympic Village, speaking to Madeleine Jenner. Now, they say that if you can't stand the heat, you should get out of the kitchen, but by the sounds of it, with a kitchen that big, you'd need a compass to get out.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
And Sarah Castor-Perry joins us now in her official capacity as custodian of the questions. While Chris and Co are away, Sarah's going to be tackling some of your questions on their behalf. So, Sarah, what cosmic questions do you have for us today?
Right, well, first off, we've got a question about the Mars Phoenix lander from Brian in Seattle. He asks, one of the instruments aboard the Mars lander has been described as sniffing chemicals after heating samples of soil up. How are the effects of the Martian atmosphere taken into account? Is the container set to a vacuum, or is the background reading from the atmosphere subtracted out? Now, we spoke to William Boynton on the show back in May about the Phoenix mission, so we decided to get back in touch with him to answer this question.
So, for those of us who didn't catch that, what was the Phoenix mission all about?
Right, well, it took off last year and it landed on Mars in May, And unlike the Viking missions, which were sent to Mars in the 1970s, its main mission is not really to seek out Martian life and extraterrestrial life, but to look to see if conditions on Mars are now or once were favourable for life. The instrument Brian is asking about is known as TIGA, which stands for Thermal and Evolved Gas Analyzer, and here's how it works from William Boynton himself. We put the sample into a very small oven, about the size of 2 drops of water, and seal it to isolate it from the atmosphere. We then flush out the atmosphere that was sealed in the oven with the sample with a flow of pure nitrogen gas. The nitrogen gas is called a carrier gas, and besides removing the atmosphere, it is used to carry the evolved vapours generated during the heating over to the evolved gas analyzer, known as the sniffer. Now, this sniffer is a mass spectrometer, a machine that you can find in any chemistry lab back here on Earth, and this can accurately tell what molecules and atoms are in the sample.
And have they found anything yet?
Well, yes, it's actually very exciting because in the last couple of weeks they have actually found concrete evidence of water on Mars, which was one of the mission's main aims.
Fantastic. Right, well, I've got an email here from Ruin in the UK, and he says, if the universe has always existed, like some people believe, shouldn't all the hydrogen in the universe by now have changed into helium or some other heavier elements? Or are there some places in the universe that make hydrogen from other subatomic particles?
Oh, I see. So what he's saying is, if there was never a Big Bang and we've always had stars around, we know that what happens inside stars is hydrogen is converted into heavier elements like helium. So if there was no Big Bang, then surely by now all the hydrogen have been used up. Is that right, Sarah?
Well, yes. I mean, the idea that the universe has always existed is known as the steady state theory, and this was developed in the 40s as an alternative to the Big Bang theory, which is that the universe came into being and began to expand about 13.7 billion years ago. The steady-state theory has lost favour since the 1960s because a lot of the evidence actually supports the Big Bang theory, particularly after the discovery of cosmic microwave background radiation, which is the sort of thing that the James Webb Telescope will be looking for.
And it's actually some of the stuff that you pick up on static on your TV, isn't it?
Exactly, and on your radio as well, yeah. But you might think that even after 13.7 billion years, I mean, that's quite a long time, you might think that the hydrogen might have all been converted, but hydrogen still makes up around 75% of the normal matter in the universe.
And that's quite a lot, isn't it? Why is there so much still out there?
Well, most of it's actually in low-density, low-temperature clouds of hydrogen, where there just isn't enough energy to fuse the nuclei to make helium or other elements. I mean, this isn't a spontaneous reaction. It takes a serious amount of energy to do it, which is why it did happen a second or so after the Big Bang, and why it still happens in stars like our own sun. The heat and the energy present is there to do it, but it just isn't there elsewhere in the universe.
I see. Well, sticking with the theme of radiation, I've got a question here that was actually submitted to us on our forum at thenakedscientist.com/forum by a member called Turnip Sock, which I'm assuming is not his real name, but I wouldn't be the one to judge. And he said that his satellite dish is full of holes, and wouldn't it be easier and cheaper to take all the holes out and just make a smaller dish?
Well, now, actually, before Chris scampered off on his holidays, he managed to pen an excellent answer to this on our forum, and he says that basically the dish is full of holes to reduce the weight and the wind resistance, aka the likelihood of it being blown away from your wall. Now, the dish works fine as a reflector despite it being full of holes because it's picking up long wavelength radio waves and microwaves. And because they're long wavelengths, they're easily reflected by the mesh of the dish because the waves won't fit through the holes. So what the waves see is effectively a smooth, flat surface which focuses the waves onto a point where the detector is positioned. And so by doing this, gathering lots of waves over a large area and focusing them to a point, you can get a much larger signal going to your TV.
And this is exactly what we did with our parabolic mirror in last week's Kitchen Science. Now, what we were doing, though, instead of focusing satellite signals, was actually focusing light and heat down onto a point. And you can actually use it the other way round and put the point source as your heat and use the dish to beam a jet of heat directly forward. Dave did this to me in his garage, and it really was quite uncomfortably warm. But isn't this the same reason why you have a gauze in the front of your microwave?
Well, yes, you know when you turn on your microwave, you can see the light on inside, but obviously the microwaves aren't coming out at you. And it's because the wavelength of the microwaves is much longer than the wavelength of visible light. So although the light can get out through the mesh in the door, the microwaves can't.
And this is why you don't cook your nose while you're watching your food cooking.
Exactly.
And speaking of kitchen science, it sounded like you guys had a bit of a storm this week.
We did, yes. I was a little bit worried at launching bottle rockets into the lightning-filled sky, but as long as they weren't attached to a copper wire, I think we're safe. But we did get absolutely drenched, yes.
Well, moving from one storm to another, I've got an email here from Shabnam in Canada, and he asks, why do thunderstorm clouds have such a clean, flat top?
Well, we actually had some great responses to this on our forum from paul.fr, but basically the story is that thunderstorms are formed of what are known as cumulonimbus clouds. Now, these grow from the billowy cumulus clouds, like those ones you see in cartoons. And these grow upwards, and the reason they do this is because if the sun heats up the ground, you get thermals, which is like warm air, and it rises, pushing up the clouds.
And are these the same sort of thermals that birds use to lift themselves really high up in the sky, and also people on hang gliders?
Yes, I mean, big heavy birds like vultures and things, ones that live in quite hot areas, will wait for the thermals to rise before they can get up in the air, because obviously they're quite heavy, so they find it quite hard to take off.
So once these thermals have lifted the clouds up, how do they get that flat top?
Right, well, they keep growing upwards, and then they reach what is known as the tropopause, which is the part of the atmosphere between the troposphere, which is the bit nearest to the ground, and the stratosphere, which is the next layer up.
And what happens there?
Well, what you get here is known as an inversion, which is where you get cold air sitting over warm air. Now, what everyone's used to is the warm air rising and therefore being above the cold air, but this doesn't happen in the stratosphere because it gets colder and colder as you go up. And this means that the clouds can't go any further as it hits the wall of warm air, so it spreads out along the top and it's very flat. Now, obviously, because the climate is very complicated, there are lots of other factors involved, but that's basically the story.
Good stuff. Well, we've had a few more emails that I'd like to mention before we run out of time on this week's show, including this one from Giuseppe Tasso, who said, "Dear friends, I'm so happy I discovered your website. It's so interesting and so nice to read and listen to as podcasts." Well, thank you very much. It's nice to hear from you. Diana?
And we've had another lovely email from Marcello, who said he'd like to drop us a note to let us know how much he enjoys our podcasts. He just discovered the site a few weeks ago and has downloaded and listened to almost all of them.
Well, that's very nice to hear, and unfortunately that's all we have time for this week. Next week we'll be back with more of the best bits from The Naked Scientist travels around the world. But get your questions into chris@thenakedscientist.com and have a fantastic week.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.